Continuing on with what happens when stars die, we are officially going to talk about my favorite thing in space. Aliens are cool, rocks from the moon are cool, but black holes, they break science. They legitimately break the rules of physics. So we're going to take a look at why a black hole happens. First, what is it? Why it happens? Are there different types of black holes? How big are they? And then what everybody wants to know, what happens when you fall into a black hole? Are they ever going to go away? How long do they last? We're going to cover a lot of stuff. So let's get started. Starting off with what is a black hole? It is a supernova remnant, most of them are. It has a very large mass with zero volume. It has zero volume because there's nothing that can push back out against gravity. So it just keeps getting smaller and smaller and smaller until you get to an infinitely small point. If you know density, it's mass divided by volume. And if your volume is zero, and you have a zero in the denominator, and you press enter on the calculator, it returns an error. This is breaking science. We don't know what happens at the center of a black hole. Let's get that out of the way right now. We can guess, we can make conjectures, but we don't know what is going on at the center of a black hole because the laws of physics that we can study and see and understand break when you get into a black hole. And so there's no way for us to know without traveling there. And if we travel there, we can never come back out. We can never even send out a signal. So there's really no way to know what's happening inside of a black hole. Obviously, they have extreme gravity. The key to a black hole is that the gravity is so strong that its escape velocity is faster than the speed of light. Now, what do I mean by that? If you throw a ball up at 5 meters per second, it's going to go a certain height. If you throw it up at 10 meters per second, it's going to go a little bit higher. If you throw it up at 100 meters per second, it's a little bit higher. Depending on how much gravity you have, there's a certain speed that you have to reach in order to escape the gravity of that object. For Earth, it's about 11 meters per second, but you have to sustain that 11 meters per second as you're escaping Earth's gravity well. Well, if you add more mass, you have to travel faster to escape the gravity. More mass, you have to travel faster. The bigger the object, the faster you have to be able to travel away from it to escape its gravity. A black hole has so much gravity that the speed that you have to travel to get away from it is faster than the speed of light. Nothing can travel faster than the speed of light. It's the hard stop speed limit of the universe, which means nothing can travel fast enough to escape a black hole. You literally cannot get out of a black hole. Black holes have two parts. The first part is what's known as the Schwarzschild radius. If you remember, Schwarzschild was the guy in that photo with Anja Hertzsprung that I showed you a few weeks ago. Anyways, so the Schwarzschild radius is the area around the black hole that you cannot escape from. If you have a sphere with the radius of the Schwarzschild radius, we would call that the event horizon. Once you travel inside of that Schwarzschild radius, you cannot get out. The other part of the black hole, that's the singularity. That's the center. That's where the mass is located. That is what breaks science. The singularity is at the middle, and we have no clue what that looks like. What's going on at the singularity? That is that infinitesimally, it's a hard word. That's a really small point. So the event horizon is just the area around that singularity. The singularity is kind of technically the black hole itself. That's where all the mass is. And then the event horizon, or the Schwarzschild radius, that's going to be the area around it that you just can't escape from because you are traveling towards that singularity. So when we talk about the size of a black hole, what we're doing is talking about the Schwarzschild radius. But in reality, the actual matter is all condensed at the singularity. So there's two parts to a black hole. There's the area of space, the area of space-time, that is affected by that black hole and you can't leave it, the event horizon, if you will. And then you have the singularity, which is where all of the matter is located, that's all smushed down together. Why does this happen? Well, if you remember, at the core of a star, when you run out of material to fuse together, and you cannot push outwards anymore, gravity is going to start pulling everything in. When a star like our sun runs out of material, it's going to pull everything in until the electrons are pushing back out. That's electron degeneracy pressure. If you're a little bit bigger, you collapse down and you push those electrons into the protons, turning them into neutrons. And then the neutrons cannot be in the same energy level as another neutron, the same area of the universe, which forms a sort of pressure that pushes out against gravity. That's known as neutron degeneracy pressure, where the neutrons can't get any closer because it would break the rules of physics. Well, if you have enough mass, you have enough gravity to take one neutron and push it into another neutron. You have enough gravity to break the Pauli exclusion principle, to break the rules of physics. You literally are taking one particle and you are putting it into another particle. And we don't really know what happens when you do that. We can calculate that that can happen, but if you take all of those neutrons and just push them into each other, you then have nothing left to push out against gravity, and gravity is going to make you even tinier and even tinier, and that's how you get down to that infinitesimally small singularity with a volume of 0. Anything in the universe can become a black hole. All you have to do is smush it inside of that Schwarzschild radius. So if you take an object and you condense it down and keep compacting it and getting the particles closer and closer together, you're going to get past that electron degeneracy pressure. You're going to get past that neutron degeneracy pressure, where the neutrons are now in the same area. So if you took planet Earth and just kept smushing it down to about the size of a peanut, the particles in our planet would be in the same part of the universe, the same area of space-time, and you would then create a black hole. The Earth would be dense enough to be a black hole, where the escape velocity is faster than the speed of light. As long as you take that object and get it smaller than the Schwarzschild radius, you create a black hole. If you took me or you and smushed it down to that many inches, roughly the size of a proton, then we would be dense enough where light could not escape. All of our particles would be in the same part of the universe, and we would be a black hole. A very tiny black hole, but we would be dense enough to be a black hole. So the Schwarzschild radius not only tells you where that event horizon is going to be located, but it also tells you the size that you need to smush something down to in order to turn it into a black hole. A lot of people are worried that Earth could possibly get sucked into a black hole. They're just all over the place, traveling around our galaxy, sucking everything into it. That's not what happens. Remember, a black hole, most of them come from a star. So if we were not being pulled into Betelgeuse, well, when Betelgeuse goes supernova and becomes a black hole, we're not going to get sucked into that black hole. You only have to worry about falling into a black hole if you are very close to it. Just like if you were very close to a star, you would get sucked into the star. So a black hole is just an object that has a bunch of mass, so it warps space-time, and if you get too close, you're going to fall in. It's not like a black hole is this magic thing that can pull things from across the galaxy into itself. It doesn't work like that. If a black hole is in completely empty space and there's nothing around it to fall in, then nothing is going to go into that black hole. That black hole is just going to kind of sit there. However, if the black hole does have other stars or nebula or other things around it, then yeah, when they get close, that stuff is going to start falling into the black hole. And if that's the case, what's going to happen as things fall in, it's actually going to start to orbit around the black hole, and that orbit will get smaller and smaller and smaller, and we call that an accretion disk. And this accretion disk are things that are falling into the black hole, and over time, that orbit is going to decrease, and it's going to get closer to the black hole until it passes this line, the innermost stable circular orbit. Once that happens, you're inside of the event horizon. You cannot leave. A lot of people ask what these jets are that are shooting out of a black hole. If nothing can escape a black hole, then what the heck is this? Well, these are basically particles that are falling into the black hole, which has a very strong magnetic field. As things are falling into the black hole, there is a lot of friction, and so they heat up and they become ionized, which means they also respond to magnetic fields. Well, a black hole, as it spins, creates a very strong magnetic field. As these ionized particles fall into that magnetic field, many of them are going to get slingshotted out of the north pole of that magnetic field. Others will get slingshotted out of the south pole. These jets have particles going a very high fraction the speed of light. And those particles were saved, if you will, because they were slingshotted out just before crossing that event horizon. Had they crossed that event horizon, there's no possible way that we know of that they would ever be able to get out. That's where these particle jets come from. Now, how big are black holes? There's really no limit. Any amount of mass can technically turn into a black hole. You guys could be a black hole if you could find some force that could smush you down inside of the Schwarzschild radius. Most black holes are produced when a big star goes supernova, so we think that the mass of most black holes are roughly the mass of a big star, because all of the matter in that black hole comes from that big giant star. A typical black hole might be about 10 times the mass of the sun, which isn't actually anything too crazy. However, at the center of galaxies, you have what are known as supermassive black holes. One of the things that helps keep all of the objects in the galaxy kind of together. The reason these are so big is because at the center of a galaxy you have a lot of material, a lot of stars, a lot of gas, a lot of dust, and that black hole is going to start having some of that stuff fall into it. The more stuff that falls into it, the bigger the black hole gets. The bigger that black hole gets, the more space it takes up. So its mass and its Schwarzschild radius are directly proportional to each other. A black hole with about 1 solar mass would have a Schwarzschild radius of about 3 kilometers. So 10 times the mass of the sun would be about 30 kilometers. 1,000,000 times the mass of the sun would be about 3 million kilometers. It is directly proportional. If I double the mass, I double the size. And for reference, this is that jet of material shooting out of the supermassive black hole at the center of this galaxy. This line right here is 88,000 light years across. Our Milky Way is only 100,000. So this line is roughly the same size as our Milky Way galaxy. And you can see that the galaxy might be smaller than ours, but those jets from the black hole at the center travel out to maybe almost 2 times as big as our entire galaxy. Those jets are absolutely huge. How do we know that they're there? If we can't see them, they don't give off any light, how could we possibly know that they're there? Well, here's a photo of one. Take a look at this nebula about 55 million light years away, and you zoom in, and you zoom in, and you zoom in. We've actually got a photograph. This is a photograph that came out a few years ago, and what you're seeing, this bright area, is the accretion disk. The black hole itself is actually not this entire area here. It's the actual event horizon is going to be a little bit smaller. This accretion disk, though, is glowing because the material is heating up, and we are actually able to see it in X-rays because that material gets so hot. Most of the light,
currently the only person in this conference.
Most of the light that comes out of it is going to be in the X-ray part of the spectrum. You can see it better with this artist's rendition, which is what's been going on over my head. And you might think, looks kind of weird if an accretion disk is just basically like a big hula hoop. What is all of this stuff going up and down? Well, that accretion disk is just the hula hoop. The thing is, the light that's coming off of that material, as it tries to escape, the black hole is actually bending it towards us. So what you're seeing here is actually the back of that accretion disk. And that light from the back of the accretion disk is bending over the top and over the bottom, which is why it looks like there is a circle here. I'm going to link to exactly what you're seeing in a Veritasium video, and Derek does a pretty good job of explaining what the heck this is a photograph of. Alright, so the first way that we know is because we actually have a real photograph, an actual photograph of a black hole. The second reason that we know is because as that material is falling in and it heats up, it ionizes the gas and it creates those jets that we talked about. Those jets, if they are pointed towards planet Earth, are the brightest objects in the sky. The brightest event is a supernova, but the brightest sustained object is those jets if they are pointed at Earth, and we call those a quasar. We can see quasars from the other side of the galaxy. Quasars are not the black hole itself, but they are the jets that are coming out of the North Pole and the South Pole of the magnetic field. And then the final way is gravitational lensing. Because they have so much gravity, they are going to bend space-time. So there is something behind the black hole giving off light, and that light is bent. We can actually determine that there is a black hole between that object and us. So as a black hole travels through the universe, the light from behind that black hole is going to get bent. Another question is, how do we know how massive they are? How big are they? We can find the mass of a black hole by studying things that are near it that it has an effect on that we can see. Just like you can have a planet orbiting around a star and it causes that star to wobble a little bit. Well, you can actually have a star orbiting around a black hole, and that star is going to seem to move. Here we have a star that is in orbit around a black hole. You can change the mass of the black hole. If you increase the mass, it's going to speed up the star, and it's going to cause the black hole to wobble a little bit less. If you decrease its mass, you're going to slow down the star, and the black hole itself will start to orbit this common center of gravity between the two. And based on the orbit of the star that we can see, we can actually calculate how big that black hole is. So by measuring the speed of the star, you can calculate the exact mass of the black hole. In this case, the star was going 118 miles per second, so the black hole is about 10 times bigger. Let's change it to somewhere here. We measure the speed of the star that we can see, and we get 243 miles per second. Based on the speed of that star, we can then calculate that the mass of this black hole is about 40 times. So by looking at things that we can see, we can calculate the mass of a black hole. Now what everybody wants to know, what happens if you fall into a black hole? Well, this is what it would look like. As you fall into a black hole, all of the light from every direction is going to start going in the same direction as you. You're also going to start catching up to that light because your speed is increasing. And when you are catching up to that light, you're going to start to become blue shifted. So the light that you're seeing is blue shifted. So as you fall into a black hole, you start seeing light from all different parts of the universe, from all directions, going in the same direction as you, and then you are catching up to that. As you get closer to the singularity, all of the light from everywhere is going to be kind of right in front of you as you catch up, and you're just going to see this bluish dot in front of you that is light from the entire universe. Weird to think about. In order to talk about what's going to happen to your body, though, you need to know about relativity. Basically, Einstein tells us that time and space are relative. They're not fixed. You can bend space, and time can speed up and slow down, depending on if you are moving, also depending on if you are near things with a lot of mass. Things with a lot of mass, like a star, even a planet, are going to cause distortions in space and time both. So a black hole is going to cause a huge distortion in space and time. We're starting to get into Einstein's special relativity, which is basically his idea of how gravity works. It's a little bit complicated, but hopefully this will help.
Number 10, special relativity. Does time fly when you're having fun? In 1905, Albert Einstein introduced the theory of special relativity, which said that if the speed of light is constant, then people must experience time differently. Which may sound impossible, but Richard Feynman later showed that you can prove it with just lights and mirrors. If you set up two mirrors, one of which had a flash bulb and a detector on it, you could build a clock which ticked every time the flash was reflected back to its original source. It would keep time perfectly, though it would make a slightly annoying alarm clock. But if you make this clock go past you very quickly, the light has further to travel. And since light always travels at the same speed, the moving clock runs slower than when it was at rest. So though time might not fly when you're having fun, a moving clock does tick more slowly than the observer's stationary clock. Which may have changed the way we see the universe, but doesn't always make for a good excuse.
A black hole has so much mass. As you approach it, time is actually going to start to slow down for you. So the closer you get to that black hole, the slower time is going to seem to run. If you had a clock on you, this is what it would look like. As you are falling towards this black hole, a few things will happen. One, somebody looking at you is going to see their clock just continue to be normal. But your clock, because time is starting to travel slower, when you are looking at your clock, it's going to start to slow down. The second thing that's going to happen to you, while you see everything blue shifted, the light that is coming from your body to that observer's telescope is going to start to be pulled by that black hole. And if it's pulled by that black hole, it's going to get stretched out and become red shifted. So an observer is going to see two things as you fall into the black hole. They're going to see your clock slow down because time starts to slow down for you. They're also going to see you start to turn red until eventually, as you cross that event horizon, no light can travel, and the last thing they see from you is the light that was given off just as you reach that event horizon. Let's watch what that's going to look like.
1, 2, 3.
The voice is
4,
going with this
5,
clock.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
We're going to drop the clock into the black hole,
2,
and
3,
it is counting off
4,
the seconds
5,
of the clock
6,
dropping into the black
7,
hole.
8,
This clock is going to start
9,
to slow down.
10, 11.
As it slows
12,
down, it's also going to start to look
13,
redder and redder and redder.
15.
Until eventually the clock seems to stop, and the last image that you see of something falling into a black hole is that object in very stretched out light, and you're going to look red shifted. That's what somebody sees when they watch you fall into a black hole. Your time seems to slow down and you turn kind of red as the light is stretched out. But what do you feel? What is happening to your body? Let's go back to gravity. Remember that gravity is affected by how far away you are from an object. The reason that we don't fly off of the Earth into the sun is because we're closer to the Earth, so we feel Earth's gravity much stronger. Well, when you jump into a black hole, let's say you jump feet first, the part of you that is closest to that black hole is your feet. And so what part of your body is going to feel the most gravity? Because it's the closest, your feet are. What part of your body is going to feel the second most gravity? Your knees. What's going to feel the third most? Your waist, and then your shoulders, and then your head. The gravity of a black hole is so intense that the force of gravity that your feet feel is so much stronger than what your knees feel that your feet actually get pulled off of your knees. And then your knees are closer than your waist. But again, gravity is so much stronger at your knees than your waist that your knees get pulled away from your waist. This is that tidal effect that we talked about, where the closer you are to an object, the stronger gravity you feel. When you jump in, the closest part to the black hole feels the strongest gravity. The farthest from the black hole is going to feel the least amount of gravity. And you are actually going to get stretched out as time goes on. The closest part to you is going to get pulled more than the farthest away part. And your body will get stretched out, or your spaceship, the closer parts, will get pulled into the black hole before the back of your spaceship. And this phenomenon is what is known as spaghettification, because you get pulled apart like a big piece of spaghetti. And your feet will get pulled off of your knees get pulled off of your waist will get pulled off of your shoulders, and then the cells in each one of your body part will get pulled apart, and then the atoms inside of your cells will get pulled apart, and you will actually enter the singularity as a stream of particles, not as a person. You're going to get stretched out like a piece of spaghetti. Black holes don't last forever. They actually evaporate. And already you're like, wait a minute, How is a black hole supposed to evaporate if nothing can escape it? The reason is because of what's known as Hawking radiation, named after Stephen Hawking. Hawking radiation has to do with virtual particles in empty space. A virtual particle is a pair of particles that just pop into existence. You have a particle and an antiparticle. And as soon as they form, they touch and they annihilate one another. And all over the entire universe, these virtual particles are popping into existence and then annihilating, and they're gone again, turning back into energy. This is one of those weird things that quantum mechanics tells us happens, even though it doesn't make sense to us. Well, if you have a particle and an antiparticle that pop into existence right on the event horizon of a black hole, the particle can fly away, the antiparticle gets pulled in. That antiparticle, instead of causing its little particle pair to disappear, is going to get pulled into the singularity and cause a little piece of mass in the singularity to disappear. Meanwhile, this particle is going to fly out from the black hole, and it's going to seem to an outside observer as though this black hole just let go of this particle. This particle is what's known as Hawking radiation, and it has to do with these particles and antiparticles popping into existence right on the event horizon of a black hole. So how fast does it take for a black hole to evaporate? Well, if you're small, you don't have a lot of stuff in you, so it only is going to take a little amount of time to evaporate away. The big ones, though, can take up to a Google years. A Google is what the search engine was named after, but a Google is spelled a little bit different. It's a 1 with 100 zeros after it. So a billion has 9 zeros, a trillion has 12, quadrillion has 15. 100 zeros, that is a very long time. So these supermassive black holes, they do evaporate because of this Hawking radiation, but the time that it takes for a black hole to evaporate, like red dwarfs will long since have died, become white dwarfs, and then black dwarfs. Like, it's way past that. Way in the future. It's hard to, I'm starting to get speechless. It's a long ways away. Just, it's in the future. A Google use from now. Here's Brian Greene, who's the #1 string theorist on the planet, telling us about Hawking radiation.
Hawking radiation is a very subtle feature of black holes that only comes to light when you go beyond Einstein's general theory of relativity and include some effects of quantum mechanics. The idea is this. At the edge of a black hole, where quantum mechanics operates, as it does everywhere else, there can be what we call quantum fluctuations, which are productions of particles that really pop out of the nothingness, exist for a fleeting moment, and then find each other and annihilate and no longer exist. The strange thing that can happen at the edge of a black hole is that when these particles are produced, one can get pulled into the black hole, leaving its partner free to fly off into space. And that particle that flies off into space is something in principle that we could see. It's radiation that comes from the edge of a black hole. So in essence, when you take quantum physics into account, black holes aren't completely black. They can radiate from these quantum processes, radiation that's called Hawking radiation.
In your own words, I want you to tell me what a black hole is and what would happen if you fall into a black hole.